Hi, today's a short lesson on an introduction to molecular compounds, interpreting chemical formulas, and the beginnings of how we're going to apply the octet rule to determine the structure of molecular compounds. Keep in mind that something that is covalently bonded involves bonds between nonmetals. It could be two nonmetals, it could be three nonmetals, it could be more than three nonmetals, but it's going to be all nonmetals. That is what it takes to get a covalent bond. And this is when you're sharing the electrons, whether equally or unequally. When you have a group of atoms combined chemically together, it is going to be a group of neutral atoms. Molecules can exist as individual units. You can have an individual unit of oxygen. You can have an individual unit of water, one molecule of water. Or you can have an individual unit, one molecule of sucrose, unlike ionic compounds, which exist as crystals. When we see a chemical formula for a molecular compound, it is the simplest whole number of those atoms in the compound. It's the actual number of atoms in that compound versus an ionic crystal, which is a ratio of the atoms in the crystal lattice. Again, just the names of those substances: oxygen, water, and sucrose. When we look at chemical formulas, no matter whether it's an ionic compound or one that's covalently bonded, when you look at the subscripts, it determines the relative number of atoms within that compound. What that means is how many moles of each atom within the compound. So let's say you have 1 mole of C2H4O2. Well, we know we have carbon, we have hydrogen, and we have oxygen within that compound. That is covalently bonded, by the way. It's 3 nonmetals. So in this one, if we have 1 mole of C2H4O2, within that, you have 2 moles of carbon, 4 moles of hydrogen, and 2 moles of oxygen. We're going to look at how you interpret PB3PO42 and C7H5NO23. We'll learn how to name those later on. So when we're going to interpret a chemical formula, we want to list first all of the atoms that are present within that compound. In this one, we have C for carbon, H is hydrogen, and O is oxygen. We're going to refer to the subscripts next to that particular atom to determine the number of atoms within the compound itself. In this case, we have 2 next to carbon, which means that we have 2 atoms of carbon. There's a 4 next to the hydrogen, which means that we have 4 atoms of hydrogen in this compound. And there is a 2 next to the oxygen, which means we have 2 atoms of oxygen. And that would be what you would write if I asked you to interpret a chemical formula. This compound is actually called lead-2-phosphate. Again, we'll learn how to do that in the next unit. Let's list first our elements. Pb is lead, P is phosphorus, and O is oxygen. We're going to refer to the subscripts next to the symbol to determine the number of atoms present within that compound. If this is ionic, this is going to be the ratio of the atoms within the crystal. Next to lead, we have a 3. So there are 3 atoms of lead. Next to phosphorus, we have a 1. However, notice that the phosphorus and the oxygen are in parentheses with a 2 subscript outside of them. Just like in math, parentheses means to multiply. So that 2 also goes with the phosphorus. We have 1 inside the parentheses, but the 2 outside. So 1 times 2 gives us 2 phosphorus. The oxygen, we're going to treat in the same way. There are 4 oxygen within the parentheses, but keep in mind that 2 also goes with the oxygen. Again, in math class, parentheses mean to multiply. So we're going to take 4 times 2, and that's going to give us 8 oxygen. Also, if you have an atom that's present in more than one place within the formula, you're going to add those together. Here we have C7H5NO23. We're going to list our atoms first. We have carbon, we have hydrogen, we have nitrogen, and we have oxygen. Next to the carbon, there's a 7. That means there's 7 atoms of carbon. Next to the hydrogen, there's a 5. So we have 5 atoms of hydrogen. The nitrogen and oxygen are in parentheses with a 3 outside of the parentheses. Inside the parenthesis, there is a 1, understood to be 1 next to the nitrogen, but we have that 3 outside. So we're going to take 1 times 3 to give us a total of 3 nitrogen. For oxygen, we have a 2 next to the oxygen inside the parentheses, but there is a 3 outside the parentheses, which means we're going to multiply the 2 and the 3 together, and that will give us a total of 6 oxygen atoms. You will have a section to do in your packet on interpreting chemical formulas. When we look at covalent compounds, one thing you're going to learn, and this is going to be a big concept for you going forward, is to understand that in nature, there are 7 elements on the periodic table that are diatomic in nature, which means that if you find them in nature in their pure form, it's not just 1 atom, it's actually 2 atoms bonded together covalently. And we'll look at our next lesson how they are covalently bonded. Which ones are they? Oxygen is one of them. Nitrogen, fluorine, chlorine, bromine, iodine, and hydrogen. I call these the magic 7, and I'll explain why in a moment. Now, if you rearrange these, you can come up with a cute little name to remember which ones are diatomic. Brinkelhoff. So bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine, when they're in their pure form, are diatomic, and those atoms will be covalently bonded. Again, it's called Brinkelhoff. It's just a quick little way for you to remember which ones they are. You can also use the periodic table to figure out which ones they are. I mentioned I call these the magic 7. So there are 7 of them. They actually make up a number 7 on the periodic table. Not all 7 of them, 6 of them make up a number 7. And they start at atomic number 7. So nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. That's 6 of our 7. The 7th one is hydrogen. So they make up the number 7. They start at atomic number 7, and there are 7 of them. What we're going to learn how to do is to make what's called Lewis structures, structures that are covalently bonded. What type of bonds are between the atoms? Are they single, double, or triple bonds? And how are those atoms arranged? Again, that will be in our next lesson. It doesn't matter whether it's an ionic compound or a covalent compound. You still have to follow the octet rule. So by either losing or sharing electrons, we want the highest energy orbital to be either completely empty or completely filled. And we do that by either losing or sharing electrons. Basically, that means to become more like a noble gas, they want to obtain 8 valence electrons in their outermost energy level. There are some exceptions to the octet rule. We will look at these in more detail as we learn how to make Lewis structures. We're going to focus first on covalent bonds, which are molecules, structures that are formed by sharing electrons, whether equally or unequally. There are 3 types of bonds that may occur in a covalently bonded structure. A single bond. Single bond is where each atom shares 1 electron. If each atom shares 1 electron, the bond between them looks like this when you draw a structure, and if it's 1 electron per atom, that's going to be 2 electrons in the bond. A double bond is when each atom shares 2. It looks like this, 2 lines. And if they're each sharing 2, that's a total of 4 electrons in the bond. And a triple bond is when each atom shares 3. It looks like this. And since each one shares 3, that's a total of 6 electrons in the bond. These structures are called Lewis structures. These are all showing single, double, or triple bonds. These structures are sharing electrons, either sharing 1 pair, which is 2 electrons, sharing 2 pairs, which is 4 electrons, or sharing 3 pairs, which is 6 electrons. In our next lesson, you're going to learn how to create these structures.